Okay, so what we're going to do is we're going to finish up with those PowerPoints and do a little Audacity example. So let's talk, we talked about periodic and aperiodic vibrations. We're going to talk about Fourier analysis, the FFT, fast Fourier transform, which is based on the Fourier analysis, and then spectra, like a discrete line spectrum versus continuous. So Fourier analysis is essentially any time you have a complex signal, it can be broken down into its individual frequency components. Okay, so I'll show you an example here. It's named after the person who invented it, which is J.B. Fourier. So here's a discrete line spectrum. We're going to talk about that, and I'll show you an example. When amplitude is plotted as a function of frequency, the resulting graph is a spectrum. Okay, so here's a waveform, right? Because time is at the on the x-axis. Now here is the spectrum of this visual. Okay, and so you can see there is specific energy here and here. Okay, so there's two frequencies in this complex signal. Okay. Remember, speech has frequencies all over the place, right? So it's a extremely complex signal, which we'll talk about. So spectrum versus a waveform, right? We just went over that. Fundamental frequency, overtones, harmonics, these are all concepts we'll talk about. Timbre is a perceptual piece of information. And don't worry about missing fundamental. That's something we'll cover later. So when amplitude is plotted as a function of frequency, the resulting graph is a spectrum, right? We just looked at that. When they interact, when sounds of frequency interact, you can see the outcome as a waveform. And again, we just showed you what a waveform was. So for complex periodic sounds, frequency of each pure tone is a whole number multiple of the pure tone. So the lowest frequency in a signal is called the fundamental frequency, or first harmonic, right? And we talked about this, I believe, on the first day. So the first bar on a discrete spectrum, which I showed you, is the fundamental frequency, and all of the integer multiples of that are the harmonics, or overtones. Sometimes you'll hear them referred to as. So this is an example of a spectrum with a 200 hertz fundamental right here. Second harmonic, third harmonic, fourth harmonic, fifth harmonic, sixth harmonic. Okay? So 200 times 2 gives you 400. So that's the second harmonic. 300 times 2, right? And so on. Now, resonance. We talked about resonant frequency. And resonant frequency is essentially the frequency at which the object vibrates at its maximum. Okay? So we'll talk a little bit about resonance. Resonance, when we talk about the vocal tract, formant frequencies for vowels, right? Those are resonant frequencies of the vocal tract. And so if a periodic source of energy is used to activate an elastic system, the elastic system will vibrate at the frequency or frequencies generated by the energy source. Okay? The frequencies of the periodic energy source are similar or identical to the resonant frequencies of that system. There will be an increase in the overall amplitude, and this natural enhancement is called resonance. So if we think about mass and stiffness as being two properties of any object, when they interact directly, you have whatever frequency this is here. This is the resonant frequency and the frequency at which you will get the best vibration. Okay, and there'll be more on this throughout the semester, but for now, that's all I want you to know. So think of resonant frequency as a natural enhancement, the frequency at which you get the most natural enhancement or vibration. So damped and undamped resonators. Bandwidth is another concept, so let's go over these. and we'll hit these again next week. But here you have two different types of resonators, right? And so the dashed line represents the this resonator that has been damped or reduced. Okay, and you can do that different ways, filtering different things, but this is a damped resonator, and this right here is undamped, so there was no dampening that occurred. Okay, so a dampened versus an undampened resonator. So when we look at this visual, you have frequency on the X, and then you have dB sound pressure level on the Y. You have, this is called a frequency response curve, meaning that this is how much energy there is by frequency. So at this frequency right here, there's not as much energy, but you go over here, there's more energy. At this frequency, there's more energy. At this frequency, there's more energy, but less over here. And we determine what we call the bandwidth of the signal based on the 3 dB or half power point. So for this particular frequency response, the bandwidth goes from here to here. So whatever this frequency is to whatever this frequency is. Because you can't, there's just reasons why you can't use this piece here, this frequency to this frequency. We use where the frequency response intersects the 3 dB down point, or what we call the half power point. Okay, this is used for hearing aids, right? We talk about in our field when we're talking about how hearing aids function, we always talk about the bandwidth of the hearing aids, and you can think of bandwidth as the frequencies that the hearing aid or the acoustic system can reproduce and send out. Okay, so think of like your AirPods or something of that nature. Your car stereo system. All audio devices have some kind of bandwidth associated with them. Okay, and we'll talk more about that throughout the semester. Now, I'm not going to do too much on this. It talks about it in the text, but when we talk about cavity resonance, the two analogies we use are the vocal tract and the ear canal. Okay, and you can think of it as a tube, both of those as a tube closed at one end. Okay, so here's some calculation. Again, I'm not worried about it. I do want you to know what bandwidth means. It's the range of frequencies to which the resonator or the filter responds, right? We talked about that. So we talked about the human vocal tract, being a tube closed at one end, has similar resonance properties to the ear canal. Okay, so here you can see. This is a new visual from the new text. So you have the vibrating tuning fork, which will play sound down into this tube. The effective length is from here to here. Okay, and this just basically shows you have a lower frequency will have this longer tube has a lower resonant frequency than this shorter tube, right? Just think of the vocal tract in that example. Now, this is how you calculate them, and again, I'm not so worried about it. But you can technically, if you know the fundamental frequency and the F1, if you will, you can calculate, this is how we calculate valve formants. But again, I don't think that's something that's super important. But again, here's the tube closed at one end. Example of the ear canal, and then here's just a random tube closed at one end. Okay, but the ear canal has the similar property. Okay, so there's that. And then I also wanted to do something with Audacity. I know my desktop looks like a mess because I have too many things going on. So in class today, we talked about a warble tone, right? And how we use it because it changes in frequency over time. And because of that, the period of the signal is constantly changing, and therefore it's less likely that we will have points within a sound treated room where we get signals 180 degrees out of phase inverted, and it reduces the intensity level at that particular point within the room. Okay, so I'm going to play this for you. I sent this to you. If you download it to your desktop, and once it's on your desktop or somewhere, you go File, Import Audio, and then find it, and it'll bring it in, and it'll look just like it does here. So let me play it so you can hear it. And I believe you should be able to hear that. So you can hear it warbling in frequency. It doesn't sound like a pure tone, which would sound uniform over time. So if I were to highlight this, drag and click and drag on there, and then zoom in, what I'm going to do is I'm going to zoom in a little bit more. And I'm going to slide my cursor here. And you'll see times where, you might already be able to see it, but let's start here. You'll see times where this, where the waveform is wider and more narrow, okay? And you'll see, and that's basically showing you that the actual waveform is changing frequency. So there you go. You'll start to see it. It'll change. So there's points there. See, they're a little more narrow there. And then if I move it back a little bit, see they're a little wider. It's not a whole bunch because it's only fluctuating in 50 hertz difference. So it goes from 950 to 1000 to 1050 hertz. But you can do this on your screen and look for times where it's a little more narrow. If you go a little faster, you can see how it's changing over time. I know it's a little hard to see, but it should do it at least 5 or 6 times over the time of the signal. And you can kind of see that where it kind of the period gets shorter and a little bit longer. Okay, so let's go back. I'll let you listen to it again. But again, this is a warble tone. Again, we use the warble tone to reduce phase inversion, 180 degrees out of phase signals in the sound treated booth. Sometimes we will use like a narrow band noise if we don't use a warble tone. And a narrow band noise is a noise, has random fluctuations, that's concentrated, let's say, around 1000 hertz. So that noise might go from 950 to 1050 hertz, somewhere in that range. And because it's random, it'll never interact like a pure tone will. So we never, ever use pure tones in through the sound-filled speakers because of the possibility of having signals interact and be 180 degrees out of phase and reduce the intensity in a particular region.